creation and the development of the first man-made abrasive or grinding material, the story of carborundum, a story of one man's inventive genius which resulted in abrasives and abrasive products, particularly grinding wheels, becoming most necessary tools in making possible higher production, greater precision. And back of this story is one of the great romances of modern industry. A romance which began in 1891 at Monongahela City, Pennsylvania, when the late Dr. Goodridge Acheson conceived the idea of creating an abrasive that would be harder, sharper, faster cutting than the abrasives made by Mother Nature, such as emery, corundum, and garnet. Here we see Dr. Acheson reenacting his first and now historic experiment by which he created an abrasive destined to revolutionize grinding and grinding methods. In his modest little shop, he set up an iron bowl such as plumbers use for the melting of solder. Into this bowl he loaded a small charge of clay and coke. Upright in the mixture he placed a small carbon rod. From his little power plant in one corner of his shop, he ran two bare copper wires. One he attached to the carbon rod, the other he wound around the bowl to complete his electrical circuit. The mere closing of a switch sent electric energy surging through the carbon rod, and thus the lid became a tiny electric furnace. After several hours of anxious waiting, he shut off the power, pulled out the carbon rod, and adhering to the end of it, he detected a few tiny, sparkling, diamond-like crystals, crystals that man had never seen before. The strange crystals looked hard and sharp, and to test them for these characteristics, Dr. Acheson collected them on the end of his pencil and drew them across a piece of broken window pane. Then the proof of the great discovery. The crystals cut or scratched the glass as readily as would a diamond. Through further experiment, Dr. Acheson created enough of the new abrasive, to which in the meantime he gave the name carborundum, to sell as a substitute for diamond dust for the rough polishing of jewels. Soon after, the uses for the new abrasive so multiplied and remultiplied that it was determined to produce it on a greatly increased commercial scale. So arose the need for improved electric furnaces of greatly increased capacity and the consequent demand for more electric power. Meanwhile, man had harnessed the mighty waters of the Niagara, and from the great generators there silently flowed thousands of horsepower of electric energy. So in 1895, the Carborundum Company began operation at Niagara Falls. And today as then, its electric power supply is generated by the swift waters of the Niagara. It all sounds so simple, this great triumph of engineering through which Niagara has been made to do the bidding of man. First, the waters are taken from the river above the falls and brought to the powerhouses below the bank of the lower river by means of this canal and a great underground horseshoe-shaped concrete tunnel 32 feet high. At the powerhouses, the water is sent surging through a series of immense pipes. The mighty force of the water, dropping from the height equal to that of the cataracts themselves, drives great turbines or water wheels in the wheel pit. The turbines drive a series of shafts. The shafts drive giant generators which create the power. Not far from the powerhouses is the huge plant where these abrasives are manufactured. These views of concrete buildings, of rooftops and kill stacks built upon the shores of the swift-flowing Niagara River give us some idea of the size of the plant, which as if by magic has grown out of that one little iron bowl furnace in which Dr. Acheson created the first manufactured abrasive. Another typical American industry developed through the inventive genius of scientists and which is playing an all-important part in providing employment for thousands. And now we invite you to make an interesting sightseeing tour of a modern abrasive plant. First to the furnace room, where one of the miracles of modern electrometallurgy is performed in these giant 2,000 horsepower furnaces. Here is one of the furnaces being loaded with its charge of the crude materials, coke, sand, sawdust, and salt. The coke to give us the element carbon, the sand the element silicon, the sawdust to make the mix porous to allow for the escape of gases, the salt to act as a flux or purifying agent. Electric energy is brought to the furnaces from the transformers to the bus bars and is then conducted through these large carbon rods or electrodes. Through the center of the mixture of the crude materials has been formed a core or pathway of graphite, along which the electric energy surges, developing the almost unbelievable temperature of 4,000 degrees Fahrenheit, a temperature at which steel and granite not only would melt, but would be vaporized. During the 36 hours of a furnace run, the elements carbon and silicon have united and formed the abrasive chemically known as silicon carbide, and which Dr. Acheson named carborundum. At the end of the 36 hours, the removable fire brick lined sides of the furnace are lifted out, the outer crust scraped away, and we have exposed the glittering, gorgeously colored crystal masses of the abrasive silicon carbide, the jewels of industry. Some idea of the sheer beauty of these crystals will be gained from the direct color views which are to follow immediately. The next step in the interesting process is to crush down or reduce the crystal masses to smaller sizes so as to permit convenient handling prior to the final crushing. The first or preliminary crushing is done in these powerful, specially designed crushers. Further crushing to reduce the crystal masses to grains or grits, as we call them, is done under these heavy Muller-type crushers. We leave the story of carborundum for a moment or two to introduce another type of abrasive required to meet certain grinding conditions. It is aluminum oxide, known to industry as aloxite. This abrasive is created in the electric arc furnace from a highly aluminous clay called bauxite, which is mixed with coke. The crude materials are loaded into the furnace and subjected to a temperature of 3,000 degrees Fahrenheit. In the furnace run of about 25 hours, these immense pigs of the abrasive have been formed in the furnace shell. Here you will see in direct color two types of aloxite. One is a delicate pink and the other snowy white. Extreme toughness as well as sharpness are the main characteristics of the abrasive aloxite. So these powerful crushers are necessary to reduce the chunks or masses, to crush them down to grains or grits. Then the millions of grains of carborundum and aloxite are graded to various sizes, from the extremely coarse to the extremely fine. This is done in these batteries of sifting machines. We call them graders. Here in action we see the screens of silk bolting cloth through which the grains are graded by sieving. It is a whole lot like sifting or bolting flour. And here for your close inspection are both fine and coarse grains, uniformly graded as to size, more alike than the proverbial peas in the pod. And now to the making of a grinding wheel. Literally millions of the accurately graded grains of either abrasive are mixed with certain bonding agents such as ceramic clays, synthetic resins, rubber, or shellac. But in this picture, we shall deal only with those wheels produced by the vitrified process and in which the bonds are ceramic clays. So then, in these specially designed mixers, the abrasive grains or particles and the ceramic clay bond are thoroughly mixed. The mixture of the grain and the bond is loaded into molds of various sizes. Then, under high pressure, the grinding wheels are formed to size in these specially designed, electrically controlled presses, thus assuring a uniformity of a given structure from wheel to wheel. And here we have the pressing or molding of a large size wheel. You see the operators loading the big mold with the mixture of the grains and bond. And it should be remembered that in this mixture, are thousands upon thousands of the accurately graded abrasive grains, hard, sharp, fast cutting, that in the finished wheel will cut just like so many miniature cutting tools. The mold is filled and the mixture leveled off. The top plate is swung into place. The iron rings which equalize the pressure are set. And the big mold is deftly rolled under the press. The table of the press is slowly raised and the mass of grains and bond is subjected to a pressure of thousands of pounds per square inch. The mold is carefully removed and we have the formed wheel ready for the next step in the process. Then these pressed or formed wheels, which are bonded with the ceramic clays, must be baked, or speaking more technically, vitrified. This is done in massive kilns, and the process is very much the same as firing pottery. The wheels are placed in protective fire clay containers or saggers, or on fire clay bats or bases, and are fired at a high temperature. During the process of firing or vitrifying, the clays melt, holding or surrounding the abrasive grains, which having been produced at much higher temperatures are not affected by the heat of the kiln, thus forming in effect a solid fused body of great strength, which is the grinding wheel. In this type of kiln, the burning cycle is approximately 2 weeks. At the end of that period, the kilns are broken open and the vitrified wheels are removed. A grinding wheel, to be safe and efficient, must run true. So the wheels on coming from the kilns are given a preliminary inspection. Then the sides are trued up with this special bell-shaped tool so that each side is in the same plane, so that the wheel will run straight and true at its ultimate high operating speeds. To give the wheels a proper bearing on the spindles or arbors of grinding machines, the arbor hole is metal bushed, the surplus metal, as we see, being removed by air-driven tools. The grinding face, or the periphery of the wheel, is also trued up, so that the wheel is perfectly round, concentric with its center, and of the required diameter. Then, after a series of close and detailed inspections, thousands of grinding wheels of hundreds of shapes and sizes and grits and grades find their way to the stock rooms, there to await the call to grind the products and tools of practically all types of industry the world over. And then on to the shipping rooms, where the grinding wheels and other abrasive products are carefully packed in barrels, boxes, or cartons. The packing is done with protective layers of sawdust to prevent possible breakage. Finally, to the waiting cars on the railroad sidings, to be shipped to thousands of industrial plants to help make possible higher production and greater precision. Little did Dr. Acheson dream that grinding wheels and other abrasive products would someday be used in every known industry when he created those first jewel-like crystals in that little iron bowl furnace. The service of abrasives in industry ranges from the grinding of the tiny balance pins in our watches and clocks to the massive parts and castings of the locomotive and the machine tool, from the grinding of fountain pens to the fluting of massive columns of marble and granite, from the grinding of wood pulp to the precision grinding of automobile and airplane parts, from the cutting and beveling of glass to the shaping and polishing of precious stones and the sanding of woods. Today, the use for abrasive certainly is as wide as industry itself. For instance, in the world of steel, the flow of the molten metal, the casting of the ingots, the rolling of the ingots into 1,001 forms, structural shapes, rails, sheets, and plates. And one of the many interesting tasks for the grinding wheel in the world of steel is the accurate grinding and perfect finishing of these massive rolls. In the automotive field, the grinding wheels of today and modern grinding machines and methods have made possible the mass production of the highly accurate parts of the present-day automobile. Here, for example, we find alongside wheels grinding crankshafts in one of the many great automobile plants, and also on such precision work as grinding the cam contours of an automobile camshaft, grinding closer than a split hair to dimensional perfection. A decidedly notable example of producing an accurate surface and high finish is found in the lapping of these plug gauges on a centerless lapping machine. Note the beautiful finish given to the gauges by the extremely fine grit wheels with which the machine is equipped. One of the comparatively recent and important contributions to industry has been the development of tool room grinding wheels. Here we have some of these wheels grinding the cutting edges of hobs, milling cutters, and spiral end mills. The grinding is done dry, yet there is no burning or drawing the temper of the delicate edges of the tools. Grinding plays an all-important part in speeding up the production of the massive machines built at this great Milwaukee plant. The few brief scenes which follow show some of the typical work of grinding wheels and disc wheels, which grind and surface various types of manganese steel castings, crane wheels, and miscellaneous machine parts. Incidentally, it is interesting to note that manganese steel is so hard and so tough that it is practically impossible to cut or finish it commercially except by grinding. The next time you play a round of golf, just remember that grinding has a lot to do with the production of your favorite clubs. For instance, here is the way that an oxide wheel smoothly and accurately grinds the heads of putters, mashes, niblicks, and other irons. The United States is known the world over as the greatest producer of all types of farm machinery. In one of our great plants, we find the operators grinding the various parts and castings of these machines with a convenient portable grinder. This, of course, is what is termed rough grinding, the smoothing down of mold marks, risers, and other surface imperfections. We journey now to the interesting plant of another farm equipment company, where batteries of grinders called cradles, equipped with oxide wheels, rough grind chilled iron plowshares. On this trip through industrial America, we stop at the plant of a steam shovel company, and we watch these big coarse-gridded oxide wheels grind the surplus metal from the manganese steel teeth of huge dredge buckets. A typical wood-burning locomotive chugs along, bringing a logging train through the Wisconsin woods to the distant sawmill. Then the logs are cut to lumber, and the great band saws which literally slice the planks from the logs must be in perfect cutting condition. So the teeth are shaped and sharpened with clean, fast, cool-cutting oxide wheels. Here we have one of these band saws in action, cutting thick planks from the log. It looks almost as easy as slicing bread with a knife. Almost as easily as a carpenter saws through a piece of wood, these extremely thin cutting-off wheels, running at surface feet speeds of more than 2 miles a minute, cut through all sorts of small bar stock of steel, stellite, brass, or bronze in round, square, or angle shapes. These wheels are bonded with synthetic resins and can be operated safely at high speeds. These same wheels are also used in the cutting of plastics, thin marble pieces, and glazed tile. One of the most interesting plants we visited with our cameras is that of a noted glass company, where we watch a skilled artisan create this beautiful example of a celebrated art glassware. Starting with a batch or gather of glass on the end of his blowpipe, we saw him fashion this crystal clear vase. And now we see him skillfully affixing the handles. In another department, we marvel at the work of another group of industrial artists who are engraving a most beautiful and intricate design on the plain or blank piece using tiny copper wheels fed with fine carborundum grains. First, a skilled and artistic designer carefully outlines with a red lead the design to be cut on this glass tumbler. The design members are first roughed out on an iron mill or wheel, the cutting agent being fine carborundum grain. Then the glass cutter, working freehand, you will notice, accurately smooths out the floral designs, the star cuts, the line patterns, and other design members in all their delicate beauty. The sanding of woods and finishing of metals call for the use of sanding papers and cloth known as coated abrasives. So we return to the plant at Niagara Falls for a moment or two to see how these products are made. First, a coating of glue on the paper or cloth backing, followed by a uniformly distributed coating of the various types of abrasive grain. Miles upon miles of the abrasive coated paper and cloth are carried from the making machines and are seasoned or conditioned in a carefully controlled atmosphere. Then wound into giant, or as we say, jumbo rolls, later to be cut into smaller rolls of standard width and into sheets. And here we have some of these coated abrasives at work, sanding the panels for various pieces of furniture. The work is being done on a typical belt sander. This is a rather interesting machine. It is called a 3-drum sander, and its function is to give a smooth, uniformly sanded surface to all types of wood. Therefore, the first drum is covered with a comparatively coarse sanding paper, the second with a medium coarse, and the third with a fine grit paper. Once through the sander, every piece is smoothly, uniformly sanded. In this particular plant is produced some of America's finest furniture, and sanding plays a most important part in its making. For example, the belt sanding of various furniture parts, such as chair back members and chair and table legs, and the delicate final hand sanding of tabletops and chair sections. The skilled operators are producing the beautifully smooth surface using the extremely fine grit, flexible finishing papers. Even your shoes know the touch of coated abrasive products, for they are used in shoe manufacturing plants the world over to smooth or buff the soles and to scour the heels of millions of pairs of shoes. Let us also remind you that carborundum and aloxite are also used in the making of sharpening stones to put keen edges on the tools of all trades and crafts and the tools and knives of the home, the shop, and the farm. We sincerely hope that you have been interested in this story of modern abrasive products, and that perhaps now you more fully realize that they play a most important role in the great romance of industry, that they are vital factors in contributing to higher production and greater precision.